One optical sorter can fire over 5,000 ejections per minute. It has about 65 milliseconds to detect, decide, and hit the right valve. Drift that timing, and purity shifts fast. Step inside. Stay on one object.
It rides the belt, rotates once, and crosses a sensor line.
A classifier calls it, and tracking follows it downstream. A few frames later, the valve row has to hit that exact piece. Miss by a few milliseconds, and the right decision hits the wrong object. Sorting isn't one machine. It's a chain. Present the stream, identify each item, track it, then move it. If any link becomes unstable, missorts rise and grades drop. So the first job isn't sorting, it's presentation. If the layer gets too thick, sensors don't see objects. They see mixtures. Overlap turns clean signatures into blended readings. So plants meter feed to control spacing, bed depth, and repeatable trajectories. They slow, divert, or recirculate until the belt becomes readable again. Throughput is always fighting controllability. Presentation is not one setting. It's a sequence of small controls that remove surprises from the belt. Feed gates stop surges from dumping a new wave onto the conveyor.
Vibratory feeders spread material so objects stop riding in clumps.
Screens split the stream so similar sizes arrive together, not stacked. Every step is designed to reduce overlaps at the sensing point. If overlaps increase, confidence drops and contamination rises. You see it in the stream shape.
Edges disappear, and targets stop looking like separate pieces.
That's why operators watch spacing and bed behavior, not just tonnage. When presentation holds, the belt becomes a readable surface.
Once the belt is stable, the line can start measuring.
Near-infrared scanning reads polymer fingerprints fast enough for production. It doesn't output a label first, it outputs confidence.
Then the recipe decides: eject, reject, or pass.
Here's what happens in plain steps. Light hits the surface as the item moves under the sensor. The detector reads a reflected pattern, not a simple color. Software compares that pattern to known material signatures.
It assigns a score, then applies a threshold from the current recipe.
Above the line, it becomes a pick. Below the line, it becomes a controlled reject. If illumination drifts, confidence collapses and contamination rises. Dirty optics shift readings.
Changing backgrounds shift baselines.
So systems monitor drift and stability, not just camera uptime. The goal is repeatable classification, not peak sensitivity on a perfect stream. But near-infrared isn't alone, because the stream isn't clean.
Labels, dirt, and moisture hide surfaces and distort signatures.
Some items are hard to read reliably at speed. So the line adds other signals, especially for metals.
This is where multi-sensor stops being marketing and becomes necessity.
Induction systems flag conductors even when optics are uncertain. They don't need a clean surface to know something is metal. Eddy-current separators then do physical separation by trajectory. They push non-ferrous metals away from the mainstream before fine sorting. That matters because metals can contaminate multiple product streams quickly.
Removing them early reduces the burden on air-jet sorting.
If loading is uneven, trajectories change and carryover rises. Clumps drag neighbors. Bounce changes where splitters cut the stream. So operators tune loading and splitter geometry to stabilize separation. You can't scan your way out of bad motion. Now the line holds partial truths about the same moving object. Optics suggest material identity with a confidence score.
Metal systems add a hard constraint, conductive or not.
The hidden mechanism is how those truths become one decision. Multi-sensor fusion weighs confidence, context, and conflict across sensors.
If optics are confident and metal signals agree, the pick is aggressive. If signals conflict, the system chooses a safer route.
Borderline items go to rejects or rework instead of contaminating product. That protects purity, but it costs yield. So recipes are engineered trade-offs, not menu presets. If the gray zone widens, yields fall and rework load rises. And that changes how the plant runs the entire day. Because now the line has to move uncertainty somewhere. Either into rejects, into rework, or into contamination. Production chooses rejects and rework because contamination is expensive.
Now comes the critical window, timing.
A correct decision still fails if it lands on the wrong object. The belt never stops moving. so the line tracks each target in motion. Encoders tie every item to a moving coordinate system. Tracking predicts where the object will be at the valve row. Here is what offset means in production.
A decision is made at one point on the belt.
Ejection happens later, at a different physical location. The controller links those points with a calibrated time delay. That delay includes processing, communication, and valve response. When belt speed changes, timing must follow the belt. If belt slip grows, the right decision lands on the wrong object. Quiet drift is the dangerous kind, because the line still looks normal. Wear changes friction. Buildup changes motion. Small shifts become big position errors at high pick rates. So plants calibrate timing like a control system, not a one-time setup. They run known material and watch where picks actually land.
They adjust the offset until the jet hits the intended target center.
Then they lock the recipe and monitor for drift signals. If drift returns, the line does not guess harder. It changes set points, slows the belt, or widens rejects.
When timing holds, purity holds without chasing false fixes. When timing slips, purity can fall while sensors look fine.
That's why this window is so unforgiving. The classifier can be right, and the outcome can still be wrong. Now the actuator has to execute cleanly.
The valve block fires short air pulses to redirect selected items.
Aim beats force, because neighbors are close on the belt. Nozzle layout and pulse timing define the ejection hitbox. That hitbox must stay stable across thousands of picks per minute. If pressure hunts, hits become random. A soft drift can look like bad sorting while sensors are fine. Blocked nozzles change jet shape. Leaks soften pulses. Response variation spreads errors across the lane. That's why plants treat air as a controlled resource. They filter it to remove moisture and oil that slow valves. They regulate it to keep pulse strength consistent. They watch manifold behavior for drops that indicate restrictions. They schedule maintenance around valve blocks and nozzles. The actuator is a wear system, so maintenance is part of purity control. When jets stay consistent, the reject band narrows. When jets drift, the system compensates by getting conservative. More rejects, more rework, less yield. Same belt, same sensors, but worse economics. If you want proof the line is working, don't stare at the belt. Watch the output grade, and watch how the plant reacts to drift. Production sorting is closed loop. Measure, adjust, verify against the spec. Here's what that loop looks like on a normal day. A sample shows a small purity drop in 1 fraction. By the end of the line, the product isn't sorted. It's qualified. It's separated into streams that hold a spec long enough to sell. And that spec is protected by timing, stability, and control loops. That's how massive sorting lines separate everything at scale.